Hello everyone, today we will model a case with conjugate heat transfer. We will model a pipe with solid walls that have thickness, allowing us to simulate the heat transfer through the solid material itself. Let's start by changing the simulation type to conjugate heat transfer, and then create our points using the coordinates in the table on screen. Now we can create two cylinders, one using the smaller radius point and the second using the larger radius point. One will be the fluid domain and the larger one will be a solid wall. Next, we will use a Boolean operation subtract while selecting the keep original box. Now press the large cylinder and then the smaller cylinder. We no longer need body 2, so we can delete it. Now we clearly have two distinct domains, the inner fluid domain and the outer solid domain. Let's name the surfaces starting with the left surface, which will be the inlet, and the opposite face will be the outlet. Now multi-select the rims of the larger cylinder and the curved surface and name it wall out. The wall between the solid domain and fluid domain will automatically be detected and set as interface. Let's move on to the mesh. We will keep the default mesh size, but we will select surface refinement for the inlet and set it to 0.03, and then we add it and do the same for the outlet and then apply and close. Let's generate the mesh now. Looking at the Y section cut, we can see the mesh is refined at the inlet and outlet. We can go to the Setup tab now. We will keep the defaults here. The heat model is enabled by default because we selected conjugate heat transfer at the beginning. Let's set up our domains. Body 1 is correctly assigned as the fluid, so we can apply it, and the outer domain is correctly identified as a solid, so we can apply it also. Next, we configure the boundary conditions. For the inlet, we set a velocity of 2 meters per second for the x velocity, temperature of 288 Kelvin, and length scale of 1. For the outlet, we will keep the default pressure outlet settings, only changing the temperature to 288 Kelvin. For the outer wall, we will set the wall type to temperature at a temperature of 350 Kelvin, making it a hot wall. Finally, let's check the internal interface. It is correctly set to perfect contact, meaning there is no resistance. We can now proceed to the Solution tab. We'll create a monitoring point located at 4 for x and the rest is 0 to track the velocity as the simulation runs. Let's run the simulation now. With the simulation complete, let's switch over to the Results tab. We'll generate a default plane for which we will set velocity and close and show. Next, let's switch to the temperature field. You can clearly see the temperature distribution. The hot outer wall forms a thermal boundary layer, transferring heat into the moving cold fluid. Thank you for watching and happy simulating.